So it's a great pleasure to have Professor Will Oliver here today with us. Thank you for coming, Will.
Thank you, yeah, for the invitation.
And so for those who doesn't know, Will is a professor of physics and electrical engineering professor at MIT, and also director of this Center of Quantum Engineering Systems at MIT too, and is a well-known expert in superconducting qubits. So, well, his expertise in this field covers all aspects of the field, no? From material growth, fabrication, design, measurement, well, many expertises, many techniques that you master, even theory.
Oh.
Well, and this expertise in his group is what allowed them to fabricate and measure these qubits, state-of-the-art qubits in all possible configurations and arrays, and as you will see in this presentation. And also, it takes a fast look at his publication records in the last years to see that he has applied these methods or these techniques to investigate all type of physics, all type of systems, or from quantum simulation, which is what you're going to discuss today, mainly, I think.
Yes, that's right. Yeah.
Error correction, even use the qubits for cosmic rays detection, or even exploring the physics of exotic materials like bilayer graphene. But unfortunately, Will is here only for one day, so he will only be able to talk about one of these topics, or maybe two. But we will be looking to learn more about your work in the future. So thanks again for coming, Will. So now the floor is yours.
Great. Thank you very much for that kind introduction, and importantly for the invitation to be here. It's really a pleasure. Good to see so many friendly faces after, well, who's counting? So many years. Yeah, and I was telling Alfredo that we were able to get some funding at MIT for some travel, and it has to be used in Spain. So I'm hoping that maybe we can have some exchanges going forward. Both ways, we can pay for both ways. So maybe this is the first of many times we get to meet. I'm going to try this fancy pointer here. I'd like to talk about emulating the Bose-Hubbard model with arrays of superconducting qubits. And please interrupt me with questions if you have any questions, if I'm not doing a very good job explaining what it is that we do. But to begin with, there are two types of qubits in the world today, and we say they're natural atoms or artificial atoms. And the natural atoms, I think we're all familiar with those. That's the periodic table. And depending on the number of protons and neutrons and electrons that we have, you have elements that have very different properties. Okay, but nature gives them to us. We don't pick them, but we use the ones that we like. Now, artificial atoms, we actually create them, and we make them from inductors, capacitors, and Josephson junctions. And again, depending on the number of these elements that we have and their particular values, we can create circuits that have very different properties. And these, though, that we can design them to have specific properties. So this isn't the entire compendium right here, but you might think of this as a Mendeleev table of superconducting qubits. And this one here on the right, which I'll talk in more detail about in a moment, is called the fixed frequency transmon. You can think of that as our hydrogen atom, simplest possible qubit. But you can see that they get much more complicated depending on how many of these inductors, capacitors, and junctions that we have. So superconducting qubits are synthetic artificial atoms, and they have properties that we can design into them. Now, before I get into superconducting qubits, taking a step back, there are many types of different qubit modalities. What I'm plotting here on the left axis is, in some sense, the error rate, the number of operations before an error occurs. That's basically 1-to-1 in the gate fidelity. So 1 in 100 would be 99% fidelity, 1 in 1,000, 99.9. you want to be in this upper right corner for best performance. Horizontal axis is the gate speed. And we know that for universal quantum computation, we need to be able to do single and 2-qubit gates. With just a handful of those, we can do any arbitrary logic. And I show this plot because you can see different modalities here. So for example, trapped ions, that's a natural atom. They have very good fidelities, but they're a little bit slow. So they're trying to get faster. Then superconducting qubits, which is what I'll talk about today in more detail, we're already pretty fast. We're trying to get higher fidelity. I'll talk about what we're doing in that area at the end. Neutral atoms, they've shown a lot of improvement over the last couple of years. It's pretty exciting. They fall somewhere in between. I also work on silicon quantum dots, defect centers like nitrogen vacancy centers. They're good for sensing. But we also have to think not just about the gates, but also about the speed of measurement and the parallelization of measurement. And this is where the artificial atoms really shine, because if you ask, say, given error correction and everything I have to do when I error correct, what's the speed of my computer? The artificial atoms will be around a megahertz, but the natural atoms are about 1,000 times slower. It's not the end of the world, right? I mean, we all have problems that we're working on. But the point is this, is that if you want to run an algorithm at a, say, a scale that's commercially viable, you're going to need a billion or a trillion operations. So for some of these benchmark applications, it may take a superconducting quantum computer a day. That's very fast. But for some of these other computers, it would take 1,000 days. That's 3 years. Now, in both cases, it's not the age of the universe, so there's an exponential speed up. But it matters because as people, we want the answer in a reasonable amount of time. And 3 years versus a day is very different, even though both are exponentially faster. So that's basically the lay of the land. Again, I'm going to talk about superconducting qubits today. I should mention, lots of really fantastic research going on worldwide. I'm not even going to try to cite everybody. And importantly, there's also photonic qubits. They're not on this chart because they're probabilistic. So with that, I'd like to get into the talk. Oh, one more slide. This is what quantum computers look like. You can see on the left IBM's quantum computer. That's this one here. This one has 430 something qubits. This is Google's, that's the old one, Sycamore processor. I have to update that with Willow now. It's both superconducting. This is a picture of a Quera atomic quantum computer, neutral atom, at least the optical table. Over here is one of IonQ's trapped ion quantum computers. It's just a black box. Everything's inside. D-Wave is in the lower right. That's a quantum annealer, superconducting. And this, of course, is not a quantum computer. You'll recognize that as the Wright Flyer. This wasn't the first time that humankind flew. We had been in hot air balloons before this. We had been in gliders before this. But this was the time when it all came together. There's somebody on board, steering, self-propelled, didn't fly very high. But when we saw this, we knew that commercial aviation would come. It was still 30 years away, but it would come. And I think that the reason I put this picture is I think that some of these other processors here have reached this point. It's still very early. It's not going to happen in 3 years or 5 years, despite the hype that we hear. Nonetheless, I think we have crossed a threshold. I'll talk about quantum error correction at the end, where we can see that, okay, it will come. And it may take a couple decades, but that's okay. All right, so with that, let me get into the talk. So superconducting artificial atoms, just a quick primer. What are we talking about? This you'll recognize as an LC circuit, inductor capacitor in parallel. It resonates. It's a harmonic oscillator, has a quadratic potential. And one of the features of a harmonic oscillator is that it has quantized energy levels which are equally spaced in frequency. What are they spaced at? Well, the resonance frequency, 1 over square root of LC. So that is a quantum circuit, but it's not a very useful one for quantum computing because we want to isolate the 0-1 transition. And if we drive 0 and 1, we want to remain in that manifold, we have a problem because we'll also be driving 1 to 2 and 2 to 3 and 3 to 4. So we have to make something anharmonic about this oscillator. We could choose the capacitor or the inductor, but superconductivity gives us a Josephson junction, and that is a nonlinear inductor. So let's pick that one. So what we see here is a Josephson junction, 2 leads that are superconducting separated by a thin insulator. We'll typically use aluminum and aluminum oxide, although we don't have to. And for our purposes here, Brian Josephson gave us these current and voltage relations for the junction. But what's important for us here is that if we combine them in the usual way that we do in electrical engineering, we can define an inductance. And what we see is that this inductance, called the Josephson inductance, is nonlinear in the current that goes through it. A linear inductor will always have the same inductance no matter what current goes through. But this inductor, the inductance changes as I change the value of the current. And that's useful. That's our nonlinear inductor. We could then ask, what kind of potential profile would this have? Well, we can do that in the usual way by integrating over time the power, current times voltage. And when we do that, we see that we get now a cosine potential. So it's no longer quadratic, it's now a cosine. And what that means is that when we instead make this oscillator out of a Josephson junction inductor, capacitor, we have a cosine, which is in blue, rather than the quadratic potential in red here. And the consequence is that these energy levels are now no longer equally spaced. And so the 0-1 transition frequency is unique from the 1-2. I can drive 0 and 1, and I can do it in a way that doesn't drive to 2. So now I have a qubit, right? And every superconducting qubit, no matter how complicated it gets, basically boils down to this idea, okay? Now, we choose that frequency to be about typically 5 gigahertz, although I'm going to show a qubit later that's at much lower frequency. But it's usually in the gigahertz range. And if you equate that to temperature, h bar omega equals kT, what is T, temperature, it's about 250 millikelvin. And ideally, we would like to be colder than that. And so we typically operate in dilution refrigerators. This is a picture of one of ours here. And this is what, roughly a meter deep, or sorry, half a meter deep, maybe half a meter wide, something like that. You can see a lot of familiar microwave, knickknacks in here, switches and attenuators and filters and whatnot. 40 years ago, this was somebody's PhD thesis. Today, they're just commercially available. We have about 12 of them at MIT campus, and I used to work at a national lab, and we have a whole bunch there that I'm not sure we say how many we have. So we fabricate these on silicon. So qubits are a silicon, superconducting qubits are a silicon technology. What I'm showing here is a 200 millimeter wafer, not this big. And there are lots of qubits on that wafer. So let's just zoom in into one of the chips. Here's one chip. You can see 5 plus signs. Each one of those plus signs is actually a capacitor. Now, usually you think of a capacitor as parallel plate, but this one is lateral. That's the only difference. So rather than this, it's like this. And the inductor, so let's zoom in on that a little bit. So here's the capacitance to ground. The inductor is here. If we zoom in on the inductor, this one is actually called a squid. It's 2 junctions rather than 1. And that's useful because if you make a loop like this and put a magnetic field through it, we can now tune the qubit's frequency. That's quite useful. So otherwise it looks like a transmon. It's just a tunable frequency transmon. And then the smallest length scale here is the junction. We're down at the 100 nanometer length scale. We've done a lot of work in 3D integration. This isn't really 3D. This is maybe 2.5D where you have bridges that go across. But we 3D integrate these. We flip chip. I'll show an example of flip chip. And we also have superconducting TSVs. I won't really have a chance to talk about that. But we're thinking about how do we scale this up in a way that's extensible. Now, we also control these using microwaves, and this is the block sphere over here on the left, or planet Earth, if you'd rather. So we start at the North Pole, and we want to do rotations to take us around the block sphere. Here we're at the South Pole. And the way that we do this is through standard in-phase quadrature mixing, or IQ mixing. The idea is that you have a local oscillator that puts out a frequency that's just about at the qubit frequency, just shy of it. And the difference is made up by this pulse, which is an arbitrary waveform, much lower frequency, and it actually gives the shape. And the way that it does it is that this mixer will multiply those 2 signals together, and out comes the result, which is a pulse, and the frequencies add or subtract. We can throw away the one we don't want. The one we keep is now resonant with the qubit. Now, the difference between the I port and the Q port, whichever one we choose, the in-phase port we will associate with the x-axis. There's no phase shift between the LO and the output. The Q port, there's a 90-degree phase shift. and we'll associate that with the y-axis. And so you can see as this video is unfolding here, this is around the y-axis. With half of the area, we do a pi over 2 pulse that brings us to the equator, and then another pi over 2 pulse brings us up to the North Pole. So this is how we do control with microwaves of this electrical circuit. And we'll basically just couple capacitively that pulse to our qubit. Okay. So with this approach, we've achieved, and I'll show at the end, almost 5 nines of single qubit fidelity and more than 3 nines of 2 qubit fidelity. What makes this challenging, and I think that this is what makes progress slow in our field, is that it takes a lot of technology to make this work and just get to the point where we can measure something. So we do a lot of work on material science, MBE. We have to do analysis, XPS, scanning electron microscopy, TEM, modeling, of course, fabrication. Here we do some bump bonding. We have to put it in a refrigerator. It takes a lot of control electronics and software, and then we get data. And often we'll find it didn't work. And then we have to try again and again and again and again. And eventually we get to this green star in the middle, but it takes time. And we're getting better at this, but it's a lot of technology, and a lot of people are working on it, thankfully. Okay, if you look at what's happened in the field from, say, 1999, when Yasu Nakamura and colleagues at NEC did the first charge qubit, to where we are today, there's quite a bit of improvement. This is efforts by people worldwide, improvements in materials, fab, and of course design. Today we're up at around, it's not really shown here, but even above a millisecond in fluxonium. And there are a number of qubits. One thing about my group is we don't really have a favorite. We work with many of them. These are some typical T2 or coherence times. And down here are some references of review papers that we've done. One is for materials, one is just the state of the community, and the other one's called Quantum Engineer's Guide to Superconducting Qubits. So if you'd like to learn more, by all means, please take a look. Okay, and so with that, let's get into some science. So I'd like to talk about these Bose-Hubbard emulators of superconducting qubits. There's lots of flavors of quantum simulation. I'll talk in a minute. I distinguish simulation from emulation, but let's just wrap it all together here for the moment. And some of them are more, you might say, materials integrated, like the materials themselves give you, the simulation just based on how the atoms align. That's one, form of this. And at the other end of the spectrum are simulators that we actually engineer quite artificially and put together. And then there's everything else in the middle. And I would say that what we're working with is somewhere in the middle of this. Quantum algorithms like trotterization and quantum chemistry would be to the right. But say twisted bilayer graphene or some of the multi-layer graphenes, where we're taking materials but orienting them in such a way that they emulate some system, that would be further on the left. So the hardware platform, there are many that do this. We're certainly not unique. And we borrow a lot from the neutral atoms and atomic physics community for sure. But our platform is superconducting qubits. The approach I would call analog hybrid, meaning this is not an algorithm that we're running to simulate a material. We are setting up the qubits and coupling them in a way that they emulate, in this case, Bose-Hubbard model. And then the system evolution is basically what gives us the answer. And so that's how I distinguish emulation from simulation. We are going to emulate with our qubits the Bose-Hubbard model. And we can then see how well we do by simulating, meaning using an algorithm on a computer to simulate the Bose-Hubbard model. And we see how close that we get. Okay. So I'm going to show experiments from two sets of qubits. Early on, it was a 9-qubit 3x3 array. And then most of the work was on a 4x4 16-qubit array. What's unique about, I would say, this platform is that we have X, Y, and Z control on each qubit simultaneously we can address them all. We have always-on coupling. We also have parametrically driven coupling. We have site-resolved readout. We can read all the qubits simultaneously in parallel. Okay, and that's a feature for us that's not necessarily available in the natural atomic systems. Okay. Okay, so let's just talk again about how we set this up. So we start with the transmon qubit that's shown here. This Hamiltonian now is an approximation where we're thinking of it as a slightly anharmonic oscillator. So of course we have what we see here is the harmonic oscillator potential, or Hamiltonian, and then we have a small correction to that, a first order correction. We couple them together capacitively. So you can see there's a voltage node here on this capacitor and a V1 and a voltage node V2. And so when voltages appear and oscillate, that's how those two qubits talk to each other. And they do that through this capacitor called CG. Okay. Now, the Hamiltonian for that has the same basic structure. You have qubit A and qubit B. Also, their nonlinearities represented by alpha, which basically means the anharmonicity. So that's the nonlinearity. And then the exchange coupling that we get, this is called transverse coupling, but it will exchange energy at a rate J between qubit A and qubit B. Okay. So what we can do is then, I mentioned this before, but if we take this junction and we split it out into the squid configuration, and we put a magnetic field through that squid, it basically looks like a tunable single Josephson junction. But by tuning the property of that Josephson junction, we can tune the frequency of our qubits. So that's the only complication here. And then you can see the yellow dots are the qubits, and the coupling capacitors are represented by these lines. And I think there's an image. Oh yeah, so then what that represents is in fact the Bose-Hubbard model, where each qubit and its frequency will correspond to the energy, the on-site energy. Then we'll have an on-site equivalent to the charging energy. And that's basically the anharmonicity, the difference in frequency. Now our 1-2 frequency is actually less than the 0-1 frequency, right? So this is attractive. If it were bigger, it would be repulsive, but this is the way it comes in. And finally, here's the exchange interaction. We're going to assume that the exchange only happens to nearest neighbors because the capacitive coupling is only to the nearest neighbor, north, south, east, and west. Okay, so here it is again, the Bose-Hubbard Hamiltonian. And we use a transmon array to represent it. And this is what it looks like. Again, we saw these pluses before, but each plus is a capacitor. You can count 4 across the top, 4 down the side. So it's a 16 qubit array. So I mentioned this already. The qubit frequency is the local site energy. The on-site interaction is the qubits anharmonicity, which is basically the difference between 1-2 and 2-0-1. And then the nearest neighbor interaction is given by the capacitance. So here's some typical numbers here. The qubits are typically 3 to 5 gigahertz in this experiment. The on-site interaction is 200 megahertz, and the exchange coupling is only about 6 megahertz. And you can see that these vary quite a bit. Importantly, we're in what's called the hardcore limit, meaning that U, this on-site interaction, 200 megahertz, is much larger than J. And so in some sense, it's a highly nonlinear system, but U is such a large energy scale that we don't even need to worry about it. We just know that we can only singly excite each qubit at a time. Okay. So one of the first experiments that we did with the system, now I'm going to step back to the 3x3 case that we started with, is called a quantum random walk. Now, if you've been to New York City or any city like New York where the roads are perpendicular to each other, then if you want to get, say, from point A to point B, you can't go straight unless you're flying, I guess. But you have to walk down blocks, right turns, left turns, right turns, left turns, etc. Okay. And so if in our qubit array that's 3x3, if we start at number 1, qubit number 1, and we want to get to the upper right corner, we have to do something like go to 2, then up to 5, then over to 6, and then up to 9. But of course, all possible paths coherently interfere with one another because it's a coherent process. They're all happening at the same time. And so you can count the number of steps it takes to get from 1 to 9. It will be 1, 2, 3, 4, no matter which way you go. Okay, and here's the data, the experiment, as well as the simulation on the right. Now, it looks very clean, and I've contrived this because in general, the random walks won't look this clean. But for a 3x3 array, the quantum interference is such that it looks exactly like you would expect, which is that I start, this is now counting steps. I start in qubit 1, 1 step, 2 steps, 3 steps, 4 steps. I'm now over at qubit 9, and then from qubit 9, I'm going to walk back to qubit 1, then I go over to qubit 9 and back to qubit 1. And of course, on the vertical axis is the evolution in time. Okay, and then the simulation is shown on the right. Okay, so as I go from 0 to 4 steps, I go from qubit 1 to qubit 9. And that is due to this Bose-Hubbard Hamiltonian, where we're in the hardcore limit. Now, again, I want to emphasize this clean of a evolution from one side to the other, we're going to see much dirtier, or not dirtier, they're quite pretty pictures, but not so simple evolution. This is only because this is such a simple system that you can really look at it in this intuitive way. Okay, so the recent work that we've done, there's a whole bunch of them here. I'm going to focus on these 4 here, and we'll start out with Anderson and Stark localization, block oscillations. I'm then going to go to the bottom 2, synthetic magnetic vector potentials, flat band physics, and then look at something called area law versus volume law entanglement, which is important for quantum computation. So for localization experiments, just to give an idea of the types of experiments we can do, we can look in 1 dimension or in 2 dimensions. And the way that we have a 2D array, but the way we can just say, pick out a 1D chain of these qubits is just to detune all the other qubits. If they're not on resonance, they're not going to talk to each other. So we detune some, and we can look at how transport goes from, say, qubit 7 around to qubit 1 and back as a function of the qubit frequencies, which we might call disorder, right? And the more we vary randomly the qubit frequencies, that variance or standard deviation, the more disorder that we have in the lattice. And what we're defining here at PR means participation ratio, but it's basically a measure of how extended the state is. Does it stay local when it's highly disordered, or does it extend across all of the qubits when there's low disorder? And you can see that this is exactly what we get, which is that there's high disorder when the disorder is strong, there's localization when the disorder is strong. That means low participation ratio, or it's delocalized. It moves around a lot. And that's true whether it's in 1D or 2D. We're doing a simulation and a theory. I wonder, what does that mean? So simulation means we know we have 9 qubits. We know the parameters. We know the couplings. We simulate the qubits we have. Theory is I use that Hamiltonian. And so this is not just testing how well we can mimic Anderson localization. It's also a test of how well do my qubits emulate the Bose-Hubbard Hamiltonian. So that's what I mean, and I'll show the simulation versus theory throughout, but that's what I mean by that. We can also do Wannier-Stark type localization, and what that means is, as you know, you put a field, you arrange the qubit energies, say linearly with a gradient like this in 1D, so that in this case, we're going to start in this middle qubit number 2, and we have a gradient in the frequencies away from that. And so what happens is that the population starts to evolve away from there, but of course it's evolving along qubits that are at different frequencies, so it can only go so far, and then it comes back again. Then it goes away, and it comes back again. And what these are is called block oscillations. These are exactly what block oscillations are. And you can see that they happen as a function of time. And the distance that one can move away before you oscillate and come back is, of course, related to the gradient. And you can see this oscillation frequency is a function of the slope. Okay, we can also do it in 2D. Just to say, and in here you even have more parameters. You could have a gradient along X and a gradient along Y and see how the evolution occurs. So for us, this was really a warm-up experiment. We're not showing anything new. I think, Anderson and Wannier-Stark localization have been studied for quite a long time. But for us, it showed that, okay, we can control these qubits in a way that actually emulates the Bose-Hubbard Hamiltonian pretty well. Okay. So we then graduated to a 4x4 array, and let me now highlight the students involved: Cora Barrett, Amir, Sarah, and Ilan. Ilan's a postdoc. Sarah designed all these chips. She's currently doing her own experiment on it. Amir is now working at Google, and Cora is a second-year graduate student. So for these qubits, the frequencies are around 4.5 gigahertz. The anharmonicity shown here, minus 200 megahertz or so. Coupling rates around 6 gigahertz. The T1 here is about 20 microseconds. It's not a world record by any sense, but it's good enough to do the experiments that we want. Readout efficiency, about 93%. And you can see the average single qubit randomized benchmarking. Whether we do it just one at a time or we do all 16 qubits simultaneously, it's about the same. Okay, and again, we're in the hardcore limit. So the first thing we wanted to do is, we're thinking, hey, let's do some really cool topological experiments with these qubits. And we realized the first thing we need to do is apply a magnetic field. But we need to apply a magnetic field to control the qubits. And so how do you then apply a second magnetic field on top of the first one and still get the physics right? And so the answer is that you have to synthetically create the magnetic field for your Hamiltonian, because the real magnetic field we're applying, that's for the qubits, right? So we can't also use that to mimic a Hamiltonian. So a lot of work, that we want to do and emulate with the system requires strong magnetic fields, and I just show a few of them here. But the point is we need to emulate a magnetic field. All right, and so this is the idea of how we do it. Of course, we know in a continuum model that we have the magnetic vector potential shown here with corresponding magnetic, momentum term. But in a discrete lattice like we have here, these are realized by Peierls phases between neighboring lattice sites. Okay, so where are we? There we are. Yep. So M is basically talking about excitation number 0 and 1. And this phase here is called a Peierls phase, and the J is the usual coupling that we talked about. Now, natively, these qubits, when they're on resonance, they have this exchange interaction that I talked about with a strength J, about 6 megahertz. And that's fine. That's with this Hamiltonian. That's if we just let the system evolve. But we can do more. We could actually drive these qubits. Well, first, we'll detune them. And then we drive one of the qubits, or both of them, but let's just focus on one, and we'll oscillate it up and down harmonically. And in doing that, we will create a coupling. We modify this coupling strength J. Turns out it modifies as a Bessel function. If you're familiar with Landau-Zener type control, this is exactly what's happening. Avoided crossing happens when these two are on resonance. And this phase then is related to the phase of the drive that we're using. So we can implement or impart a magnetic, or a phase, a Peierls phase, in this coupling term. And that's what we need to do. So we set this Peierls phase by parametrically driving pairs of superconducting qubits. And we therefore can emulate what in the magnetic vector potential in a continuum model. Okay, so that's in a nutshell what we did. And let's just show that it works first off. So here we have 4 qubits in a loop, qubits 1, 2, 3, and 4. We start with all the population in qubit 1, and we're not going to do anything. Okay, we're not driving these. So the flux through the loop, which we'll call phi, is 0. So we're not doing what I just described. And what you can do is then follow the excitation from 1 to 4 and then back to 1, just like we did it with the 3x3 case. And what you're seeing here is the population in any one of these 4 sites. And the 4 sites have different colors as a function of time. So, this would be site 1, this color is site 2, 3, and 4. If you just focus on the orange, you can see that the orange starts with no excitation, then gets a full excitation, then no excitation, then a full excitation, etc. And transiently, sites 2 and 3 are passed through to get to 4. So here's a little simulation of it. And you can see that you're on the left, and then you go through to you're on the right, you go back to the left, and that's what happens in time. That's when, we just couple them directly with capacitors, and we don't do anything special. But we can do the same thing, but what we're going to do now is we're going to put a magnetic field of pi, or magnetic flux of pi through this loop by driving qubits 1 and 2 parametrically like I described. So that creates a phase. That phase we set to pi. And what you can see now is that the excitation never gets to 4. It actually destructively interferes because one pathway gets a minus sign, the other one doesn't. I can't get to 4, and I just go back to 1. That's all I can do. Okay, so this is called Aharonov-Bohm caging. Right? Somehow caged it into qubit 1. So we can then, do this as a function of phase. We don't have to choose just pi phase shift. We could choose any phase shift that we want. And what we see then is this type of pattern. And now this gets a little more complicated. We're varying that phase, or the flux, from minus pi to pi. Should be symmetric about 0, which it is. And we look how this unfolds as a function of time. And we're looking here at the population. Okay, this is the simulation of the experiment with the qubits I've got. And this is the theory of this model, which here is called Harper-Hofstadter model. And you can see that, okay, it's not perfectly the same, but it actually mimics this pretty closely. So this array of 16 qubits, or in this case just 4, mimics this Hamiltonian, emulates it fairly well. Now, the nice feature, I would say, of superconducting qubits is that we can actually measure all 4 of these qubits simultaneously. And so you can look at any time for any flux, you can look at all 4 qubits and come up with these interference patterns directly. That's a nice feature. That's actually very hard to do on a natural atomic system. You would have to repeat this experiment over and over and over and over again. Okay. So we can look at what happens in larger rings, not just 4. So here we are with 8. Or sorry, not 8. Let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, 8. And we start on the left, we go to the right and back. We've imparted the phase in the same place. So we're plotting as a function of that flux. And you see the experiment, the simulation, and the model. And again, looks pretty decent. Yep. Yeah, so that's right. So in simulation, we know that we can measure each qubit's parameters. We can measure each qubit's coupling. Like we characterize that all at the beginning, and then we simulate that specifically. And in the case of the model, we're just using what I would call the textbook model that we're trying to emulate with these qubits. And then we ask, what would that predict? So qubits, of course, have dissipation, they have decoherence, right? The model doesn't include any of that, right? So the model looks very clean, as you can see. And then the simulation looks, okay, maybe there's a little bit more level broadening. And you get a bit more, maybe the interference isn't quite perfect here, whereas it looks perfect here. So there's small discrepancies, but the general pattern looks pretty good. But we really care, if we want to use quantum computers in the future to emulate real systems, we want to know how close are we actually getting to that model, right, that we're trying to mimic. Okay. And then at the bottom, you can see we've done it for the entire perimeter of the 16 qubit array. Okay, so now I'd like to demonstrate gauge invariance. So we know that if we sum up the magnetic field, or the phases around a loop, that should be the magnetic field inside our, or the magnetic flux inside the loop. But all that matters is the sum around the loop is the same. So for example, here's the experiment we just talked about as a function of magnetic flux shown here. So the magnetic flux in the loop, the phase is here, the magnetic flux in the loop is phi. I could put it somewhere else, and as long as I go in the same direction around the loop, that pattern should look the same, shouldn't change. And so we changed the position of where we applied our phase, but when we look at the experimental results, they look the same. It's invariant. Didn't matter where I put the phase, as long as around the loop, I add up the total phases, gives me the total same flux, should be the same plot. I can put it there. Looks similar. I can divide it into 3 pieces that are a third as big each, and I get the same plot. So this is exactly what you would expect, because all 3 of these, when you go around the loop, add up to phi. But let's say I did this. Let's say that I put it in 2 places, but one with a oriented with a plus sign here, and I come around, and with this one, I get a minus phase. Those 2 phases cancel, And now nothing happens, even though I am changing the phase on both sites because they're equal and opposite. I don't see anything, right? So this is showing that what we are, the synthetic magnetic flux does obey gauge invariance. We expect that, but it's a good thing to check, right? Okay. So we know from Maxwell's equations, I guess electromagnetic duality, that we should be able to create an electric field as well, not just a magnetic field. Okay, so the idea here is let's take a 1D chain. We looked at a smaller version of this experiment before. So we have an excitation on this qubit. We've detuned all the qubits that have a light color, and we're just looking at the 1D chain around the outside. And so if we put that excitation there and ask how far did it step as a function of time, we get this experiment, again, the simulation and the model. But again, if we now add in this Peierls phase, we know that the electric field is the time derivative of the vector potential A. And so we can use a letter F to represent the synthetic electric field that is the time derivative of our Peierls phase. And so when we do that, we can create again, this gradient, let's say, so Wannier-Stark type localization. And you can see now that the excitation really stays where it started in blue. And it tries to go away, but due to the gradient, it has to come back. And so we get these block oscillations again. And that gradient that we're applying is an electric field gradient. So by using a Peierls phase, we can basically make both a synthetic magnetic field and a synthetic electric field for this array of qubits. Okay. So the next step would be to now emulate something else. And so here, what Ilan did is he basically took the array and he detuned the qubits. So he now has what he calls a rhombus lattice. So you can see there's a rhombus here with a phase, a magnetic flux phi, a second rhombus, and a third one in a chain. And if you just look at the band structure of this in some idealized sense, when the magnetic field or magnetic flux is 0, you get one flat band. There's 3 bands total because there's 3 rhombus structures. But if you then go to different phases, eventually at pi, all of the bands are flat. And so we can mimic a flat band condensed matter material in this simple way, a very simple case. But you can ask, does this exhibit the properties one would expect for a flat band system? In particular, the velocity in a flat band system of particle should be 0, say an electron. And so we would expect localization, for example. Okay, so we string together these 2x2 plaquettes or rhombuses to emulate the 3 unit cells of a rhombus lattice. It always features one band, but when phi is pi, all the bands become flat. Okay, so let's see what this does. So I'm not going to talk through the whole thing, but let me just say that it's the same experiment again, where the flux that we change is on the left or vertical axis, but it's the same flux in all 3 rhombuses. Now, the detail is we apply it on one of the legs here, but it doesn't matter which leg we apply it on. What matters, of course, is just what the value is, but it's the same flux through each loop. And what you can see is, that when you look at, does the excitation, which starts on the left side, so this first, we're looking at the qubits population as a function of time here, then the second qubit here, third qubit, and then all the way at the right. And what you see is when it's pi, when the flux is pi, no excitation gets to the right at all. Never makes it. It can't, because it's a flat band system, and there's no, in some sense, there's no velocity to get from the left to the right. So we can define a conductivity of moving from the left to the right, and we can see that that conductivity has some non-zero value for fluxes until we get close to pi. And at pi, basically, it doesn't conduct. It doesn't go from the left to the right. Okay. You can even define a localization length in terms of how far did it go, how many steps did it take. And you can see that, again, when we get to pi in the flat band region, there are no bands available to move. And so it basically stays localized on the left on the blue qubit. Okay, so this is, there's a lot more into the paper, but this is basically the key result, which is that we can mimic these flat band type systems. Okay. So we're going to now use the same qubit lattice, but we're going to change what we're testing. And so this is a story about entanglement and how entanglement exists in a large number of qubits, or maybe not large, 16 here, but in principle, a quantum computer will have thousands, millions of qubits. And the question is, how do you quantify in any way the entanglement? And are there different types of entanglements? And we'd say, yeah, of course there are. And we're going to explore two types, one which is what we call area law type, and the other which is called volume law type. And for the upshot here is that for quantum computers to be powerful, they need the volume law type entanglement. The area law type entanglement isn't going to cut it. Okay, so you care about what type of entanglement you have. It's not that all entanglement is created equally. So we know in classical thermodynamics that basically entropy arises from uncertainty in the exact state of our physical system. And in quantum mechanics, entropy arises due to entanglement amongst subsystems, in this case of qubits. All right. And so the idea is that, if you have a product state of these 8 qubits, let's say, where there's a system A and a system B, and I can write it as a product state, and I trace out or I measure the B side, my A side is still pure, right? Because it's a product state. So within A, there may be entanglement. Within B, there may have been entanglement. But because it's a product state, I measure B, I still have A, and it's untouched. But if the entire system is entangled, A is entangled with B, then if I trace out the B qubits, I'm left with a mixed state in A, right? Because they were intimately related to begin with, and by collapsing one side, I've affected the other side. And the degree to which this has entropy now is an indication of the type of entanglement that existed there. So quantum entanglement with a quantum system, or quantifying entanglement with a quantum system is achieved by measuring the entropy of the subsystems. And so we use this entropy definition called second Renyi entropy, which is defined here, minus log base 2 of the trace of the subsystem density matrix squared. So if there's no entanglement, that entropy will be 0. I'm left with a pure state. There's no. And for maximal entanglement, we would say that it equals V, where V is going to be subsystem volume. And you can see that here V is equal to 4. And basically the number of qubits within the subsystem, we're just going to count that up and going to call that volume. I didn't define these terminologies, but this is what they call it. Now the area then, if volume is basically the number of qubits, then area is going to be the number of connections along the outside edge of this, so around that square. So here the area would be 1, 2, 3, 4, 5, 6, 7, 8. Here the area is actually larger than the volume. Okay, but these are the rules of the game. Okay. So this Hamiltonian, this Bose-Hubbard Hamiltonian, even with just 16 qubits, has a lot of states, 2 to the 16. And so the energy spectrum of this lattice is quite large. And you can see that if we look at the energy as a function of the number of excitations, not just 1 or 2, but could have all 16 qubits, could have 8 qubits. We are limiting it again to the hardcore model. So each site can only have 1 excitation, but with 16 qubits, I can have up to 16 excited qubits. And what's plotted here is the density is the number of eigenstates that exist. So as you might imagine, the highest number of eigenstates would be right in the middle, where half of the qubits are in their excited state, the other half are in their ground state. And so that's the way it is. And the lowest energy and the highest energy is also with those 8. Okay. And so the scaling, the entropy scaling with the size of the system looks like this. So with volume law, if you're in the center here, you have volume law entanglement. It's entanglement which is across the entire system, essentially. But if you're at one of the edges, this is basically what we call an area law type entanglement. And again, the power of quantum computing is realized when we have volume law type entanglement, not area law. And so we want to find ways to actually characterize for a system, is this entanglement volume law or is it not? Okay. Yep. Yes. Oh, you could ask, you could ask what are the, what are the eigenstates for these, with these 8 qubits, right? How many entangled, or how many eigenstates do I have of that system at that point? And, it's a very, very large number. You can see it's like yellow means 100. Oh, so out of the 16, let's say I'm going to choose 8 of those 16. And which 8 do I choose? Well, there's so many different permutations, right? Yeah, that's right. Yeah, that's why it's such a large number. It's also why 0 and 16 aren't a large number, because there's only one way I can excite all 16. There's only one way I can keep all 16 in their ground state. Yeah, thank you for the question. So what we're going to do, so I didn't tell you what the challenge is. Let me do that, see if I can go back. Yeah. So you could imagine that, these eigenstates, there are many of them, and they're also very close to each other. And so how do I make a single eigenstate, right? That's really hard. And this is what have prevented people from doing this type of experiment in the past is, people have been thinking, how do I make one eigenstate out of this very dense system of eigenstates? And how am I sure that I got the one? And so we cheated in a sense. And I'm going to tell you how we cheated. We just said, let's not do that. Let's do something else. What we did is we started with all qubits detuned so that we could put them into their ground state and make sure that they don't interact. And then we brought them all onto resonance, and we drive them all at the same time. And I'll show what that does in a moment. I just want to say what we're doing. So we evolved the system by driving all of the qubits when they're on resonance. We drive them with a strength omega. And we can even detune the driving frequency. That's important. So the qubits on resonance bare may have this frequency. We can drive them at a frequency that is not that frequency, right? That's a parameter we have as well. We'll then do tomography through measurement. Because we can only measure in one basis, we will do a rotation first to that z-axis from wherever we are, and then we make a measurement, and that's how we make measurements in other bases like x or y, even though our measurement is always in z. Okay, so the entire protocol is 100 microseconds long, but the business of it is really this 270 microseconds where we're driving it, which is about 10 over j in time. All right, so what does this, again, this is the Hamiltonian, rewritten in the hardcore limit. We're going to do one more thing. So we looked at this Hamiltonian already, but we're going to move to a rotating frame. And in the rotating frame, we still have the coupling between neighboring qubits, but the drive detuning appears here, right? And then the driving strength is related to the anharmonicity. So I'll tell you what this means. This is the actual Hamiltonian, but let me explain what it does for us. So if we drive on resonance and we ask which section of this spectrum are we exciting, you can see that we're driving essentially the volume law section. We're not getting any one of those eigenstates, but we know that the eigenstates we do get, together are going to all be of this type. Now, as we detune in frequency, you can see that this moves away from the center, and then eventually, for strong detuning, we're now we only excite eigenstates at the edge, which are area law-like. And this is basically how we cheated. We said, we're not going to try to get one eigenstate. We're just going to excite a bunch, which are of a certain flavor. Okay. So it's superpositions of many body states, and it will therefore have indeterminate particle number. It's not just the 8-qubit eigenstate. it's going to be a superposition of 6, 7, 8, 9, 10, etc. But we know that it's going to be a superposition of a certain flavor of eigenstate. Okay. So to summarize, we drive the system off resonance by an amount delta, and this allows us to switch from area versus volume law type entanglement. Now, when we drive with a strength omega, the strength of the drive, this is basically the size of the region and the number of excitations that we have. If we drive weakly, we don't excite very much. We're going to stay on the left side of this. And if we drive really strongly, we'll move to the right side. Lots of excitations. Okay. Now, one interesting feature, which I'll just point out without saying too much, this is how it evolves in terms of the number of excitations as a function of time. And you can see that, you know, for a very strong drive, which would have a fast Rabi frequency, if you want to think of it that way, you can see that we actually hit, on average, a fairly high number. And then it oscillates a bit and eventually saturates. What's interesting is that you get these probability distributions in the number of qubits that's excited, and it takes a Poissonian shape. It's a Poissonian distribution. And so there is a connection here to coherent states of, you know, an analog to coherent states of light, but it's in this 16 qubit array and the number of qubits that's excited, depending on the detuning and the strength. I won't go into more detail here, but it's an interesting connection, and we talk a lot about it in this experimental paper and also a companion theory paper. And you can see the different distributions that look Poisson-like, and they move to the right or to the left. And eventually, in some limit, we get to what looks like a Gaussian. Okay. So the entanglement scaling behavior, again, the volume law is related to the size, the number of qubits in a region. The area law is related to the boundary and the connections. So you can count, you know, again, just same exercise we did before. This, if we chose these qubits to be our subsystem, that area is 4, and then there are 4 boundary regions. So that's the volume is 4 and the area is 4. The next one over you can see is 4 red, so the volume is 4, but the area is 8, etc. So this is basically how we count. So in the experiment, we did 163 subsystems like this, just chosen randomly. And then we reconstructed the subsystem density matrix and extracted the entropy versus subsystem size, and this is what we got. So based on our detuning, which is shown here, when we have 0 detuning, we expect volume law-like, and that's exactly what we measured. Very little area law-like characteristic in terms of the entropy. And then when we detuned in both directions, you know, symmetrically with what you'd expect for ensemble average noise, we get something that looks more and more area law-like as we move to the edge of this diagram. So we can observe this transition from a volume law-like scaling to an area law-like entanglement scaling by measuring the entropy of these subsystems over many, many such subsystems. We can look at the scaling as a function of the subsystem size, and it basically increases, as you see here, but the scaling for area law increases more slowly than it does for volume law, and that's what we expect. And this scaling law is called a Page. That's the jargon, I guess. This guy Page wrote a letter about it in '93, and so you do expect this linear scaling, but the peak ends up being much higher for volume law than it does for area law. And in fact, the peak basically follows the entropy should very closely follow the number of qubits involved up to n over 2. The peak again would be for n. Okay. So this is just exercising to show that it makes sense and it works. So this transition, you know, was seen for the first time by our group and also by a group in Innsbruck that did it with trapped ions around the same time. Okay. Any questions on that before I change gears entirely? Yes. Yeah. Yeah. That's right. So there is an edge effect that happens here, right? You're absolutely right. Yeah. And so, you know, in some sense, we can account for that. In another sense, it is the system we have. Yeah. Ideally, you would do this with, no boundary, right? Yeah. Okay. Just a couple more slides, if that's okay. Is it too late? 5 minutes? Okay. I'll take 5 minutes. One of the many types of superconducting qubits, fluxonium, is one that we've been working with a lot lately because it has millisecond coherence times. So it's got very good coherence, and it also has very good qubit fidelities. So we're seeing here single qubit fidelities around 4 nines and 2 qubit fidelities around 3 nines. The question is, we wanted to understand how could we make it better, and in particular for the single qubit. Let me skip through this. This is just what it looks like. There are two qubits and a coupler there. But if you want to increase your single qubit fidelity, and you're a superconducting qubit, you're limited by coherence, right? So coherence is taking a tax in time. So the shorter you can make your gate, the less you have to pay in tax. So ideally, if your gate was instantaneous, there would be no penalty. You could have a high fidelity. The longer your gate, the lower the fidelity, because we're limited by coherence. And so the idea is that if we can increase either the coherence times T1 or T5, that'll make a better fidelity, or decrease the gate time. So what happens when you decrease the gate time? Well, if you decrease it enough, you start to see problems that are related to the rotating wave approximation. So there's a counter-rotating wave. It's there. We ignore it. We call that the rotating wave approximation. It's still there. So in the qubit, it knows it's there. And it starts to lead to Rabi oscillations that don't look like sinusoids. Okay. This becomes a problem because it's related to how fast you're going compared to the frequency of the qubit. And fluxoniums tend to be low frequency qubits. So the upshot to the story is that we were able to increase the fidelity to almost 5 nines by accounting for this co-rotating effect first and then doing it in a better way. And I'll just give a highlight here. But if you have a physical spin, like an electron spin or a nuclear spin, the x, the y, and the z, those are real spatial coordinates. And so, in fact, we talk about the polarization of light as being circularly polarized if, in fact, it's oscillating in that xy plane. It's traveling this way, and the electric field is oscillating around. But in our qubit, we don't have it. It's not real space. We have charge and flux. Those are our conjugate variables. So we thought, well, why don't we just drive both of them at the same time and create what looks like circularly polarized light, circularly polarized driving, by precisely timing the driving of both our charge and our phase in time. Okay, and that's what we did. So if you don't do that, if you just drive linearly, which is what our field has done in superconducting qubits since the beginning of time, basically, is you drive along just the charge axis. I drive it sinusoidally. And we know that, just through some simple math, that you can write this as a rotating wave in one direction and a counter-rotating wave in the other direction. When you add those two together, you just get the linear drive. Okay, so that's the origin of this rotating and counter-rotating term. You go to a rotating frame, which means you decide to lock in on one of them, but then the other one counter-rotates at twice the frequency. And then you just say, well, just ignore that one. That's the rotating wave approximation. Okay. So the problem is we want to go fast. And that's exactly when you start to see this pollution from the counter-rotating wave. So again, as I mentioned, what we do is we actually drive both charge and phase at the same time so that we can create a circularly polarized light. There is no counter-rotating wave in this case. We exercised it. We can, of course, by choosing the relative phase between these drives, we can actually reproduce the linear drive, and you can see the effect of the counter-rotating term right here. The steps of the counter-rotating term. But we can basically turn it off by going to creating this circularly polarized drive. We can make it worse, right? We can actually accentuate the problem. But the point here that we want, this is just to exercise it for the paper, but where you want to be is in a circularly polarized driving, where there is no counter-rotating term. And by doing that, we could actually get our fidelities up to 4.5 nines, as we would say. And what we're showing is circularly co-rotating drive, just flux, just charge. You can see charge here is a little bit worse, and that's why that pulled down the circularly polarized drive is because we have to drive both charge and phase. One of them was a little bit worse, and so the two together came down. Okay. So that's great, but it requires two coaxes. So the question is, can we think of the problem this way, but not have to drive two things at the same time? And the answer is called commensurate driving, which is basically a story about carrier envelope phase. And that was the Nobel Prize 2 years ago, right? Which is if you have these really, really fast pulses, if you care about energy, you care about how much of the oscillation is within that narrow pulse that you have. Usually we don't think about it because we'll have hundreds of oscillations within our envelope. But let's say you had only one or half. Then clearly where it exists within the envelope, the carrier envelope phase, matters a lot. Here's an example of how much it matters. You could ask, I want to go from North Pole to the equator, 90-degree pi pulse. I'm going to do it fast, and then I'm just going to shift in time where the same phase or the same pulse occurs, right? And you can see the oscillation of my local oscillator is in gray, and my envelope is in the color. And whether I choose blue or orange, I'm going to get a very different rotation because the amount of energy under the pulse is different. And again, usually you don't see this because usually you're in a regime where you have so many oscillations that shifting effectively doesn't change the energy. And so your pulse duration here, how many Larmor precessions it does, is usually much larger. But as you go to faster pulses, this becomes an important error channel. Upshot, and I'll just stop here, is that if you time things properly, what we call commensurate pulses, you make sure that the phase is the same under the pulse that you're trying to drive or shifted 90 degrees for a Y pulse, rather than just randomly timing it as we typically do. We'll call that incommensurate. You can actually fix the problem. And that's where we were able to get up to almost 5/9 of fidelity. Why can I do that? Well, you're still going to have an error due to the counter-rotating term. I'm going to be somewhere along this trajectory here, but I can, let's say it was 85 degrees, fine. I just turn up the amplitude a little more until it's 90. What's important is that because it's commensurate, the counter-rotating effect always comes in with the same phase. I just need to time it at, turns out to be 1/2 of the Larmor period when I apply this pulse. And if I do that, the counter-rotating term gives me the same error every time. I correct for it with amplitude, doesn't matter. And I only need one coax cable, which is nice. Okay, and so with that, let me just, the results are shown here. And we really are limited by coherence until we get to the very, very fast pulses, and that's what we're focused on now is, if we want to get down to 5 nanoseconds, how do we make that truly coherence limited? I appreciate my students because they're very honest. It's not 5 nines, it's 4 nines plus an 8. We're going to try and get that last 9. Okay, and so I don't have time to talk about this. I was going to talk about the Google result, fantastic result, where they actually showed error correction beyond threshold for the first time. Be happy to talk about that with the students at our Q&A session. I worked with Google about 20% time, and we're really happy to see this result. First time in any platform, by going from distance 3 to distance 5 to distance 7, you're adding more qubits. You're adding more noisy qubits. The error rate is going down. That's amazing. First time it's ever happened. Of course, it has to happen if we're going to make a scalable quantum computer. So this is a really big result. But I've gone over. So let me just acknowledge my team at MIT, the Engineering Quantum Systems Group, my former team at Lincoln Lab, with whom I still collaborate closely, and all of our sponsors. And thank you for your attention.
Thank you very much, Will, for this nice presentation. So we have time for questions.
Well, thank you very much for the talk. It was absolutely impressive. I mean, I was wondering if there is any possibility to do fermionic emulations or simulations, or just, because of the nature essentially of your qubits. I mean, you're stick essentially to bosons.
It's very hard. We're thinking hard about how to do that. There are algorithmic approaches to simulation, but we're starting with fundamentally a bosonic excitation. So there's transformations one can do to make it look like a fermionic system, but it requires lots of gates. And we're just not at the stage yet where we can do those gates. Now, with error correction, yeah, we would be in the limit where we could, basically have all the time we need. Not quite, but almost. But how to emulate that in a NISC era? If you have a good idea, we'd love to talk. Thank you.
No questions?
Thank you so much for the beautiful talk. So it's related to question by Juan Carlos. So now in the synthetic gauge potentials part, so all of these results are now a single excitation on one qubit, and therefore you are just exploring the single excitation subspace of the whole thing. And so I was wondering, can you now excite all of the qubits but one, so you will now explore now the propagation of a whole instead of the propagation of an excitation? And
yes, great question. We have a student thinking about that. Sarah, who I called out earlier, she designed all these chips, and she's doing an experiment now where she's going to look at not the hardcore limit, but actually look at first, one excitation, two excitation. I think she'll probably go up to 3 or 4 on each site, and she wants to do mod insulator superfluid type emulation. Now, we have very few qubits, right? So this is going to be trends as opposed to a fully many-body system. But we can, we've done enough, theory that we know we can start to see the trend, even at 9 or 16 qubits. So that's what she's working on. We're also working on maybe related to that doublon type excitations where you have 2 excitations and you see how that 2 excitation moves around on the lattice. So we're just starting to exercise and see how it all works. Yeah, thank you.
You mentioned that you have to repeat the experiment very, very many times to get one plot or one result. Was that correct?
No, well, what I was suggesting is that we do, because at each point in that 2D plot is an experiment. And not just one experiment, but an ensemble averaged experiment. Okay.
So,
but we can measure all 16 qubits at the same time. And in an atomic system, typically they measure 1 atom at a time. So not only do they have to fill out the 2D plot, but then they multiply it by the number of atoms they want to measure. So that gets prohibitive, right? So they typically will take a snapshot of the whole thing, but they're not measuring, they're not doing tomography on each atom individually. Yeah, that's what I meant to say.
What I wanted to ask in that direction is, your measurement is destructive? So
It's what?
Is destructive?
It is projective.
Or projective, yeah?
Yeah, it is projective, and it's also QND.
Could you do some kind of weak measurement to get some information about dissipative time evolution?
We can. We haven't done it, but people in the superconducting qubit community have done weak measurements and looked at trajectories in a phase space of how that evolves to projection over time. We haven't done those experiments. It could be interesting. Yeah.
Thank you very much. I wonder if you could make the point about the materials which you use for the qubits, because I saw that you are using titanium nitride. Is this right?
Yeah, so in these experiments, it's all aluminum. So aluminum and aluminum oxide is our barrier. But in our other works, we've used a lot of nitrides. We use niobium nitride, tantalum. We're starting to look at tantalum nitride. We haven't really done that yet, but that's on our list. And the idea is to look for materials which may have favorable meaning low numbers of defects or clean interfaces that we can create. Who was it? Somebody said the surface is the devil made the surface physics or something like that. So I believe him, because it's all about surfaces, whether it's the substrate to metal or metal to air. We have to be very careful when we fabricate these. So anyways, that's the material science, is exploring some of those interfaces, and then also can we, you might think I'm going to use tantalum for my qubit. Okay, you can do that, but you might put down a seed layer of something else to make better tantalum, or you might cap it to make a better tantalum. So the majority is tantalum, but it's not all tantalum, right? Those are the kinds of experiments.
Thank you.
There is no more question. Maybe I have one.
Sure.
So the principle, your model is, well, you map into the attractive Hubbard model. So when is the fact that the U is negative going to play a role? No,
Yeah. So with transmons, we can't do it, but with fluxoniums, we can. So I've got students who are working on making arrays of fluxonium qubits. And then fluxonium is basically a double well potential type. So you can go from a region which has highly negative to something which looks like a transmon with highly positive, just by tuning the qubit frequency. So
okay, it's
yeah.
With fluxonium, you can lower the qubit frequency and
Well, yeah, you're right. So you could, in some sense, with a flux qubit, you get a certain anharmonicity at each qubit frequency.
Mm-hmm.
But if you make a double loop flux qubit, you can tune both sigma z and sigma x. So you could, in fact, just sit in one place at one bias point and tune the qubit frequency, which basically would tune this U between plus and minus. No free lunch. You have another channel for decoherence. So we may not start there. We'll probably start with the one where it's, qubit frequency, whatever one we choose has a particular anharmonicity, plus or minus. And they're locked together, which one we get. So, yeah.
It's amazing in any case. Well, if there is no more questions, I think we thank Will again.
Thank you.